So this is an apartment building having 33 stories. Floor to floor height is 3.3 meters. Total height of the building is 108.9. So the length of the building is 36 meters. So the building will be like this. .36 meters by 34.5 meters. And floor to floor height is 3.3 meters. Total height is 108.9 meters h. And when you consider other parameters, one is this is B, is D, and B over D ratio less than 1. So because of that, the coefficient for leeward coefficient is minus 0.5 and windward coefficient is always 0.8. So those are the values, basic values that we can obtain. And first option. So the length of the building is 36, D is 34.5, and natural period of vibration has been given in x direction as 3.4 seconds, y direction as 3.8 seconds. So when you take the reciprocal of that, you can find the natural frequency as 0.294 and 0.264, and both are less than 1 Hertz, which means the building, we have to consider the dynamic effects. And the basic design speed is 38 meters per second. So the wind speed at the top of the building, we have to find the wind speed at the top of the building. And for that, we have to use the terrain multiplier. And the terrain multiplier for a height of 108.9 is about 1.17. 1.17. So we'll use that value, 1.17 multiplied by 38. So we'll be using a value like 44.46 meters per second as the wind speed at the top of the building. And to determine C dynamic value, we have to get all these values sorted out. So the first one is when you want to determine the C dynamic, S is taken as 0, because that's given in the description, saying that when you calculate C dynamic, deflections at the top of the building, single value of C dynamic shall be used with S taken as 0. So S is taken as 0. So S is considered as 0. So we get S is 0. So the height H is 108.9 meters. IH is the turbulent intensity, and turbulence intensity depends on the height and the terrain category. So height is 108.9 and terrain category 3. So it will be a value in between 0.15 and 0.166. So I have used a value like 0.164. 164 for a height of 108.9 meters. 0.164. You don't have to interpolate very accurately, but if you interpolate reasonably, then you can get a value. If you want, you can interpolate exactly, but it will not make a big difference. If you get a reasonable value, it would be okay. So I use 0.164 for turbulent intensity. And so GV is a peak factor, and that is to relate the average effects to the maximum effects. So that factor is considered as 3.4, and it's a fixed parameter. And then this parameter that they obtain with the wind tunnel testing, the turbulence length, and that is given by 85 times h over 10 to the power 0.25, and our height is 108.9, so you get 154.4. So here you can see, here you get C dynamic is a function of turbulence intensity, and also it's a function of GV, and then BS, and you can see the background factor. BS is a background factor, and that deals with the static response of the building, and that value depends on what we call LH, or the turbulence length. So BS is a function of this. So what you have to do is just substitute in these values, and here BSH is the width of the building, and BSH means the average width of the building, and here we have a constant width for the building, that is 34.5 meters. So once you substitute, you get BS as 0.719. So you can calculate the value of BS as well. And then there's another factor called height factor, and the height factor is considered as 1 because it's equal to 1 plus SOH squared, where S is 0, because of that HS is 1. And then, so that is the static part of the equation. Now we are looking at the dynamic part of the equation, which has a value called VR, GR, SET, and damping. And some of these parameters actually depend on the natural frequency of the building. So some of these parameters depend on the natural frequency of the building. So you can see C dynamic depends on the static and dynamic response. So this is the dynamic response of the building. And so here you get GR. Peak factor for resonance response, 10-minute period, is given by this equation 1.2 plus 2 log E 600 NA, where NA is the natural frequency of the building in the along direction. And here you have to be a little careful because this log E 600 N. So the GR value is 1.2 plus, you have to substitute for the natural frequency in the along wind direction, and the natural frequency in the along wind direction, x direction, is 0.294, across wind direction is 0.264. So when you calculate that value, it's 3.4, and you can see all these parameters are given in the form of equations, which means you can easily write a spreadsheet program for calculating this. So most of the design engineers have a spreadsheet program. So once you plug in the numbers, you can straight away get the answer, because most of these parameters can be defined at the beginning of the spreadsheet. Then, you know, there are two parameters. One is called size effect, S, and that depends on the dimensions of the building. So here you can see dimensions of the building and the natural frequency of the building. And so here you get the height of the building, here you get the breadth of the building, and then it also depends on the velocity under which you are doing the calculation. So you get the velocity also in the same term. So once you substitute in this one, we know all these values. NA is 0.294, height is known, the width of the building is known, GV is known. GV is we calculated it. It is given. It's a fixed value 3.4. IH we consider as 0.164, and the velocity at the top of the building is 44.6. So you'll end up with 0.0834 S value. 0.0834 S value. So we know GV, we know BS, HS, GR, S. What we don't know is ET, and we can calculate that value also. And ET is given by this particular expression which depends on a non-dimensional quantity called reduced frequency. And N is given by this equation. N is NaLH 1 plus GVIH over V design theta. So that is the design speed that we use. Theta means the orientation, but in Sri Lankan conditions, I told you earlier that we don't consider the orientation. It's the same value. So N is equal to 0.294 plus 154.4. 1 plus GV is 3.4 into IH is 0.164 divided by the velocity. So you will end up with 1.59 for N. And then when you substitute for ET, that is this equation, you will end up with 0.066. Then the other important parameter that we have to determine is the damping, and the value of damping depends on whether you are considering the ultimate limit state or serviceability limit state. So here we are calculating this to determine the ultimate load. C dynamic is determined to find the ultimate loads. So because of that reason, you will find that the damping ratio that we can use is 0.03. So we have to use the value of 0.03 for the damping. And if you are using, if you are doing a calculation for static conditions, then we have to use a value of a lesser value, as I explained earlier. So you'll get this value 0.03 for damping. So now we can substitute in for all the values. GV is 3.4. We calculated this as BSS 0.719 and SS 0.083 and ES 0.066. So in this particular example, GV and GR both are 3.4 and the damping ratio is 0.03. Then when you calculate the C dynamic value, we get a value slightly less than 1. So which basically indicates that for the particular wind speed that we considered, the dynamic effects are not very critical. So if you want, you can use C dynamic as 1.0. C dynamic as 1.0 and do the calculations. And if you consider a higher wind speed, there's a chance that you might end up with a value greater than 1, say you might get 1.05 or some value, if the wind speeds are higher. So this way you can see whether the dynamic effects are critical or not. And in this particular example, although it falls out into a particular height range, but still the dynamic effects may not be that critical. So because it's less than 1. And generally we use C dynamic as 1 for all the small structures. So even in other structures, we should be using 1. But if you get an answer more than 1, greater than 1, then we have to use that particular value, which means all the wind effects have to be multiplied by that particular parameter, so that you will end up with a slightly higher value than what you calculate without C dynamic. Is that clear? So then you'll ask why we calculated C dynamic. The reason is most of these C dynamic values are needed to calculate the alone wind acceleration as well. So most of these parameters will appear in that equation as well. So let's see how to determine the alone wind acceleration. And in this particular building, the dynamic effects are not that critical. So the alone wind acceleration is given by this particular equation, where here you can see the mass of the building, height of the building, and then resonant component of peak base bending moment. And we see how to calculate that particular value. And you know force is equal to mass times acceleration. So when you want to determine the acceleration, divide the force by mass. So that's why the mass comes here. Force is equal to mass times acceleration. So acceleration is force divided by mass. So you get this equation on that basis. And so we'll see how to calculate this particular component, because all these values can be easily determined because now we know the method. But when you are calculating this acceleration, I told you earlier that we use different wind speeds, because you know we don't have to determine the acceleration when the peak wind speeds are acting. So we generally determine the acceleration for slightly lower wind speed. So generally a wind speed like 25 meters per second can be used when we determine the acceleration with a lower return period. So the alone wind acceleration is given by this equation. So wind force on the windward side depends on the height. Therefore, you know, now here you can see we have an equation to determine this component, the peak base moment. So here you can see it's a function of wind speed, and it's a function of wind speed for the windward side, but it is not a function of wind speed for the leeward side. Here you can see we design theta is inside sigma, here it's outside sigma. Then you will ask what's the reason for that. I explained it earlier. Here you can see wind speed is variable on the windward side, it's fixed on the leeward side. So The wind component can be taken out of the equation on this side, but this side it has to be part of it. So because the wind is variable like that, like this, I would consider that as, constant over certain heights, so that I can do the calculation easily. So I will consider that up to 30 meters it is constant. Up to 60 meters again is constant. Up to 108.9 meters also is constant. So I consider that although it varies like this, I will say that, it varies like this one, so that I can do the calculation easily. Otherwise, I might have to use a spreadsheet and do the calculation because the wind speed is varying all the time. So because I'm going to do a manual calculation, I'll divide the building into 3 components over the height. So I'm going to have 3 different velocities over this, whereas on the rear side, it's a constant velocity. Rear side, it's a constant velocity, or leeward side, it's a constant velocity, whereas on the windward side, it is variable. So now we'll see how to do this calculation. So windward force, the wind force on the windward side depends on the height. Therefore, 3 regions have been considered. So in this example, 0 to 30, 30 to 60, 60 to 108.9. So basic design wind speed is 25 meters per second, since under serviceability conditions, a lower return period like once in a year or once in 2 years can be used for wind-induced accelerations. So the terrain multiplier we have already determined earlier. The terrain multiplier for different heights can be obtained. So we'll use terrain multiplier here. 0 to 30, you can see at 30 it's 1, here is 0.83, so I'll use a value like 0.94 for this 0 to 30, a constant value like 0.94. Then 30 to 60 meters, I'll use a constant value like 1.07, and with 108.9 it's slightly more, but I will use 1.16 for the upper part of the building. Is it clear? I'm not using the full value at 30 meters, I'm using a slightly lower value than the value at 30 meters, considering the fact that it's a variable force. And I'm trying to use some kind of average value. And for 60 meters, I'll use the coefficient applicable for 50 meters. For 108.9 meters, I'll use the coefficient applicable for 100 meters. So that's how I have calculated the average effect of this variable action. Is that clear? So for the terrain multiplier, I'm using 3 different values. And based on that, I can find the design wind speed. And then I can also find design speed squared, because this pressure is given as Q is equal to KVS squared. So, and also in this equation also what appears is Vz squared. So I have calculated that value as well. So now we have to find this C figure windward is 0.8, this is 0.5. So we know those values. Now we want to find this particular value. And so then it says the width, distance, dz. So this is a kind of integral. And so basically, if I show you that function, it is like, so we have the breadth B, and we want to find velocity squared B Z dz. So this can be found because now we have made it constant, B constant. So we can say B Z dz is equal to B Z B times the corresponding height multiplied by Z bar, the distance to the centroid. So I can say V Z B Z dz is equal to the area of this multiplied by the distance to the center, and the area of this multiplied by the distance to the center, and area of this multiplied by distance to the center. So I can say this is equal to sigma of this, because now I am not considering a variable force, but I am considering a constant force over a certain height. On the other hand, you can write input all these values onto a spreadsheet and write the equation, so that spreadsheet will automatically calculate this part. So this value is given by, so integral of, here you get sigma over h. So is the integral this bz z dz. So this value is equal to, first we get the breadth of the building, so I can take it out, 34.5, and then I get V design theta z squared 841 multiplied by the height component, height of the section, that is 60 meters to 108.9, that is 48.9 meters, multiplied by distance to the centroid from the bottom. So what I have to do is, the width is constant, so I can take it out, 34.5, and then the velocity corresponding to this is constant. The velocity squared is 841 over this height, that is 841, and then this height is 48.9, and then the distance of centroid is 60 plus 48.9 divided by 2. Then we come to this component. Here the wind speed is 712 and the height of the section is 30 meters, and distance to centroid is 30 plus 30 divided by 2. And similarly, I can write the equation for this part as well. So you can see this is a variable function over the full height, but to get an answer easily, we have converted it to constant values, representative constant values. And then to get the total bending moment, I'm considering the three components, and then I'm calculating the total bending moment due to this particular set of loads. And so that's why I have considered this as 48.9, this as 30 meters, this as 30 meters. And also I have considered different V squared values for these three different regions. Is that clear?
Yes.
Yes, sir.
Right. So similarly, on the leeward side, it's constant. So I can just 34.5, take it out. and Vh squared is what is the value that depends on the at the top of the building, the 841, multiplied by the total height multiplied by distance to centroid 108.9 divided by 2. So here you can see we can easily calculate these values when we consider that the average values over 3 regions, and if the building height is more you can even consider 4 regions. But if you look at this function, you can see it does not vary much as you go up. So as you go up, it does not vary much, and it varies to a certain extent here, but the effect of that, the wind forces acting in the lower part of the building is very small because we are considering a bending moment. So any inaccuracy here will not have much effect, and here it's not varying much. So even for a slightly taller building, you can consider 3 regions, and if you want to be more accurate, you can consider 4 or more regions. But the answer might not vary very much. So instead of a variable force, I have considered a force that varies in stepwise. So basically in this equation, you can see this part is done, this part is done. Then we know windward, that is windward coefficient, that is 0.8, leeward coefficient 0.5. But again, you can see leeward coefficient is minus 0.5. So here you get minus, here you get minus 0.5. So that means the effects are added up. Although it says this minus this, leeward effects are suction, whereas windward effects are pressure. So then they have to be added up. So although you can see it talks about the difference, what actually happens is C figure leeward is minus 0.5. So you will find that this and this will be added up. Then we can substitute for these values, rho air, GR, IH. But only thing is, we have to see whether we can make use of the earlier values or whether we have to calculate the new values. And you will feel that some of these actually depend on the velocity. So because of that reason, some of these parameters need to be calculated for the new velocities. So get these. And then we also have a term called mass, M0. And M0 is the mass of the building in kilograms per meter, where the meter is in the vertical direction. So that means the weight of the building per meter height, weight of the building in meter height in kilograms per meter. Mass of the building per meter height in kilograms. So the unit is kilograms per meter. So how do you calculate the masses? We know in a building, the mass comes from the slab, columns, beams, finishers, services, all can contribute to the mass. So what you do is we generally calculate the total weight of the building, and then total weight of the building per floor, and that includes the weight of the shear walls as well. And then we divide it by the floor to floor height. So when you do this calculation, typical value for the weight of a floor per meter height generally varies between 250 to 300 kilograms per meter squared for a typical reinforced concrete building. So I will consider that for this particular building, because it's an office building, the weight will be on the lower side because most of the partitions would be lightweight partitions. So I'll use a value of 250 kilograms per meter squared. And when you multiply 250 by 34.5, multiplied by 36, you will end up with a flow weight of 310,500 kilograms per meter height. Can be obtained by using 250 kilograms per meter squared per meter height value. So 250 multiplied by 34.5, 250 multiplied by 34.5 multiplied by 36 gives you 310,500. But when you are doing an actual problem, you have to actually calculate the weight of the columns, beams, slabs, the shear walls, finishers, all add them up. Then the load that you get will be in kilonewtons, so you have to convert it to newtons, then to kilograms, and then divide the whole value by floor to floor height. Then you can get this number. And then if you divide that number by the area of the building, then you can see where you stand, whether you are below this value or within this range or outside this range. You can also see. But this is the general range. And you will see that, I'll show you later, that this mass of the building is also a very important parameter when it comes to the calculation of the acceleration. So with all this, now we can substitute in the equation. And here you can see rho air is 1.2 and GR is 3.4. This is 0.164. I have used the same values like S and B. BS is okay. GR doesn't depend on the velocity, but this depends on the velocity. So I think I should have actually calculated S again, that I haven't done. So I have used this S value 0.083, and N also should have been calculated. So I think I have not done that. I used the above values. So I should have actually calculated those values, but I have not done that. This one I think I have done that. Yes. This one I have done that, but in this particular example, I think I have forgotten to do that. So here there's a small mistake. I'll correct that mistake in the note before I upload it. Here I should have actually calculated this S and E for the new velocity. S and E should have been calculated for the new velocity, right? So that is something that I forgot to do. So basically, let's assume that these are correct. Then you have to look at this, what do you call, the damping ratio. And damping ratio is given here. Now we are looking at the acceleration of the building. When you are looking at structural damping for solid state, when you are calculating for deflection, 0.01. For reinforced concrete structures, for deflection it is 0.015. For acceleration it's 0.01. So I have to substitute 0.01 for damping. So this is 0.01, and here you can see 1 plus 2, 3.4 times 0.164, and here you can see this is 0.8 times 161.5, plus 0.5 times 172 into 10 to the power 6, And finally, it gives a value like 0.0411 meters per second squared. So this way, there's a small error, but let's assume that we can correct it. You can see the acceleration is given as 0.0411 meters per second squared. And generally, any acceleration less than 0.05 is not felt by people, unless you are very sensitive to any movement. Generally, it's not felt by people. And the maximum acceleration is considered as something like 0.152, not 2, here 0.15 to 0.2 meters per second squared. 0.15 to 0.2 meters per second squared is considered as a limiting value. This is not 2, I'll correct that also. 0.015 to 0.2 meters per second squared. So here you can see the value is 0.04, but we can go up to 0.15 to 0.02 meters per second square can be considered as limiting values. So basically, this is the way that we calculate the alone wind acceleration. So first we calculate these parameters in the alone wind direction for the wind speed that is applicable to us. And that is the mistake that I have done, because I have not calculated those values. Some of the values are dependent on the wind speed that I have not recalculated those. But once you calculate those values, and once you calculate the base overturning moment by using the wind load on the structure, then you can work out the acceleration of the building. And if this acceleration is more than 0.2 meters per second squared, then you will think that it's not a good building to go ahead, because once the building is constructed, there's a chance that in a windy day, people will feel the movement of the building, and when they experience this too often, they will not like it. So they will say, it's difficult to work at a table because it's moving too much. Then you will find that you can't rent the building. So which means there's no point in constructing the building, and which also means it's better to do these calculations right at the beginning, so that we can so it's better to do the calculations right at the beginning, so that we would know where we stand with respect to the wind-induced acceleration of the building. So this is a calculation that is advisable to be carried out at the beginning of a design. So any questions on this? Any questions? So this is the way we calculate the wind-induced acceleration of a building. And these are all empirical formulae based. And you can see, because it's all equation based, you can easily write a spreadsheet so that these values can be these calculations can be carried out automatically the moment the basic parameters are given to the spreadsheet. Is that clear?